Now that we've talked about and introduced the idea of arrays, now we're going to talk about one of the most useful things that they can do, which is beam steering. We talked before about the graphical representation of the sinc function. I'm drawing it with 4 side lobes, which would be for 5 antenna elements, but obviously you can vary the number of zeros to increase or decrease n that way. And we talked about how this sinc function maps onto the circle of visible space that you would see for a polar plot. So a polar plot represents visible space. Well, this rectangular plot of the sinc function represents sine space, also sometimes called cosine space, because psi is proportional to the direction cosines. Now this polar plot that's in visible space, the way that we drew it last time, it ends up, since its origin is right below psi equals 0, that means that the main beam always ends up right here at the top of the circle. What if, instead, we could shift the origin of this circle? What if we moved the circle over by a little bit, drew the same circle, but now its center is here? Well, now the main beam, rather than being pointing up, is going to map down to right there. And now our main beam on this array points sideways. You can slide this circle from one side to the other to move the position of the main beam to whatever angle you want. Mathematically, the way that we do that is by adding a progressive phase shift to all of the individual element contributions. So instead of just being e to the j k d cosine theta, it's now going to be e to the j k d cosine theta minus cosine theta naught, where theta naught here is the steer angle that we want to point the beam to. So now, instead of all of these terms having 0 phase when theta here is equal to 90 and the argument of the exponent becomes 0, now they're all going to have 0 phase when cosine theta minus cosine theta naught becomes 0. And so they will all be adding up in phase in some other direction. Physically, what that looks like is, let's say that we've got, oh, I'm sorry, there should be an n here, e to the n jkd in the top. That's a really crucial thing. Physically, what this looks like is, let's say that we would like all the contributions from our individual array elements to add up in phase to something that's up in this direction at some angle, theta naught. Well, if they're all excited with 0 phase, the contribution from the top element will get there first, because it has a slightly shorter distance to go. And the contribution from the bottom element will get there last, because it has a slightly longer distance to go. So a phase shift needs to be applied so that the top element is delayed relative to the lower ones. So each one of them, if the separation is d and this angle is theta naught, then this length and also this length are, well, the length is d cosine theta. So the phase associated with that length is kd cosine theta. So the nth element has a phase delay of nkd cosine theta. That's the progressive phase shift that you need to delay these elements by. That's assuming that this is element 1 and this is element 3. The bottom one is element 1 and the top one is element 3. So based on that stuff, if we write down the sinc function of our new beam-steered pattern, the sinc function now becomes sine of big N kd over 2 cosine theta minus cosine theta naught divided by sine of kd over 2 cosine theta minus cosine theta naught. In general, we can say that the array factor of any array is usually a function of the following form. It's always got a constant multiplied by a direction cosine. So this is a direction cosine, so it might not be cosine theta anymore. It might be the direction cosine for x or the direction cosine for y also. Plus delta, where delta is the phase shift. C here, the constant, in the case of this sinc function, is nkd over 2. And delta is nkd over 2 cosine theta naught. Now if we take these facts and we apply them again to the, so if we want to go back to the graphical solution, here's how you do it. You define yourself a new variable, zeta. And zeta is going to be equal to that constant times cosine of your direction cosine, times your direction cosine plus delta. Which, if we write it out, that's n over 2 times the psi variable that we were using before, which is n over 2 kd cosine theta plus beta. Then we plot our sinc function, or whatever the function is that determines our array factor, as a function of zeta. So if it is a sinc function, it's going to look like this because all sinc functions look like this. So step 1 was plot f of zeta. Step 2 is draw the circle. The circle should have radius c, and it should have its origin at zeta equals delta. So if we just kind of arbitrarily pick some values for that, let's say that delta is this much. So we'll draw the circle there, and we will choose its radius to be that big. Then, same as before, we propagate or we project all of the zeros and maxima from the function onto the surface of the circle, preserving the heights of the various lobes we can then draw the radiation pattern for this antenna. Like that. And because we've shifted its origin by adding that delta term, we can also shift the direction of the main beam, which is how beam steering works. And you can see in the pattern that we've generated here, by sort of my randomly chosen radius and delta values, we actually have a main beam and a grating lobe. Now, which one is the main beam and which one is the grating lobe is really just a semantic distinction, but in general, the main beam is going to be the one where zeta is actually equal to 0, and the grating lobe is going to be any version, any lobes, any major lobes where zeta is not equal to 0.